Okay, hi everyone. So today we will continue our second class for instrument competency. So let me share my screen. Okay, so I'm just going to recap back on whatever that we have learned last week. So we have learned about gas chromatography, how is gas chromatography looks like, the instrumentation, and then we we also covered around some comparison of chromatographic techniques. What are the other chromatographic techniques that are available, and what are we focusing on in this course? So, for example, in this course, we are focusing on gas liquid chromatography. Okay. So, and then we also have looked at on what are the important parts, what are the important instruments in gas chromatography, and then how does the gas chromatography looks like. Okay, so and then we also continue with how gas chromatography happens, what are the separations, how are the separation happens. Okay, so basically separation happens on the interaction of analytes on stationary phase as well as mobile phase. Okay, so these are the schematic diagram, or this is the schematic diagram of a GC instrument. So basically you would have a carrier gas. So carrier gas, usually the carrier gas is helium, nitrogen, and then hydrogen, and also sometimes it's purified air. And you will also have this regulator, flow regulator pressure. Okay. So you would also have this flow regulator pressure where it regulates the flow of this carrier gas. Okay. And also we also look at the what are the injectors have the injector modes and the columns where the stationary phase resides and the detector. Okay, so yes, as I mentioned, these are the real GC instruments, where are the injection ports and how autosampler works, and then these are the ovens which houses the column. Okay, and then we also covered on the GC lines, gas lines configurations, where they all of the gases are being filtered using all of these trapped, because we only want a pure gas going into the GC. Okay, and then we also covered in detail on what is carrier gas. So carrier gas, as I mentioned before, is only to transport your sample into the GC column. It is chemically inert and it does not affect your analytes. Okay, so the choices of carrier gas, as I mentioned, is nitrogen or helium. And then these are the examples of flow rate whenever that you are using column, capillary column or packed column. Okay, and then we move on into the injector. So injector, we also covered the two modes, which are split modes and splitless mode. Okay, and then so these are the schematic diagram on how split injection happens. Okay, as you know that we depend on the ratio that we have set, and then a splitless injection, uh, which only specific towards analyzing trace compounds. And then these are the this is the splitless injection mode, the schematic diagram where this is important, where the split vent is closed. Okay, so for today, I'm going to share with you on the oven. Okay, the oven is a controlled uniform. It control the temperature. Okay, this is the oven, which houses the column. So in this oven, which houses the column, a controlled uniform temperature is required. Means that whenever that you have set the column, for example, you need to set the oven temperature to be, for example, 250 Celsius. So this temperature needs to be controlled, okay, and uniform across the duration of analysis. So the column temperature would be slightly above the boiling point of the sample results in an elution time of 2 to 30 minutes. So for example, as what you have learned in the injection pot, usually we set it at 50 Celsius, much more higher kan? 50 Celsius much more higher than the least volatile component. But for the oven, we set it also slightly above the boiling point of the sample results, which in this case, we also can use this principle. Okay? So that is the oven, which the important thing for the oven is that you need to make sure that it is controlled uniform temperature. Okay? Right. So for the oven, there are two separation modes. Okay. Separation modes, the two separation modes are isothermal and program modes. So what does it mean by isothermal and what does it mean by program modes? Okay, isothermal, a fixed temperature is used during the separation. Means that for this isothermal modes, you would set it, for example, you would set it at 200 Celsius only for 30 minutes. Okay? So you would set it at 200 Celsius for 30 minutes for the duration of analysis. But for program temperature, the temperature is set to be like, for example, you set it at 100 Celsius for 1 minute. And then you would increase the temperature to 150 Celsius for another 2 minutes. You set it to become 300 Celsius for another 10 minutes. So this the meaning of program temperature. The temperature is increased continuously or in steps as separation proceeds for sample of wide boiling range. Okay, so you need you set this program to make sure that separation happens effectively. We will look into detail on on how program temperature happens. Okay, right. So basically, there are two separation modes that you need to know, which is isothermal. Isothermal straight away fixed temperature. Program temperature, you set the program to become whatever that you want that fit your analysis. Okay. All right. So we are going to the next slide. For simple samples, separation may be carried out under isothermal condition of constant temperature. So for simple samples, maksudnya contohnya you are analyzing hydrocarbon from C2 until C8. So basically the temperature range is not that high or not that wide. So you can use isothermal conditions where you set the temperature of the column to become constant. For samples with wide range of volatility, you need to use temperature programming. You need to set your program. You need to set out your program. Okay. So to enable volatile compound to be resolved at low temperature, an elution of later less volatile compounds to be speeded up as the temperature increases. So, on how are we going to understand on how temperature programming works? So, what you need to do is that, okay, for example, you have, how can I say this? You have two compounds, okay? Two compounds. Okay, two compounds where the first compound, the boiling point is 100. And then the second compound, the boiling point is 200. Okay, so if you use isothermal conditions, you set it up to become 250 kan? Because it needs to be much more higher than your least volatile. So if you use 250, for isothermal, katakanlah you set 250 Celsius for this compound, so your chromatogram would become, it should be like this. So the first compound, the second compound. So the first compound and the second compound tends to combine because both compounds vaporizes at the same time. Okay, it vaporizes at the same time means that it will elute also during the same time. So because it's not that far, so what I mean is that when you set it up at 250 straight away, this vaporizes, this also vaporizes. Okay, so for this kind of chromatogram, it's not that good because you don't have good resolutions. Resolutions means that the peaks are not well resolved. So for example, this is an example of well resolved peaks. Means that maksudnya there are some ada penjarakan di sini. Okay, kalau yang tidak elok tu dia macam ni. Penjarakannya sikit sahaja. Walaupun ada, tetapi it is not that well resolved lah. So separation itu perlu berlaku secara efisien, yang mana that's why kita employ temperature programming. Okay, so how are we going to use temperature programming? Okay, what I can say is, what I can explain is that as simple as, for example, okay, so for these two compounds, you already know that the first compound is 100 Celsius, the second compound is 200 Celsius, the boiling point. Okay, so you would set it to become 100 Celsius. Okay, 100 Celsius for the first minute. Minit pertama, you set at 100 Celsius. And then you would ramp. Okay, kat sini kita ada RAM value. RAM value adalah you akan RAM ni adalah because for example for 100 to go to 200 you cannot go instantaneously. You need to have a RAM. Maksudnya from 100 to 200 there will be an increase. Kan, nak naik daripada 100 ke 200 ni perlu ada peningkatan suhu. So peningkatan suhu itu, how are you going to set the ramp? Okay, so for example, you say that, the ramp is going to be 20 Celsius per minute. Okay, so you set the ramp after this 1 minute of 100 Celsius, you need to set ramp 20 Celsius per minute. So, it means that dekat sini ambil masa berapa minit dah? Dekat sini. Dekat sini is going to take around 5 minutes, betul? To reach 200. Betul kan? 200, 100 bahagi 5. Yes. So 5 minutes. So during this ramp, okay, dia naik 120, 140, 160, 180, and then baru 200. So when it reaches 200 Celsius, you do something like, okay, at 200 Celsius, I want it to be constant for another 2 minutes. And then end the analysis. So the overall analysis, when you total it up, is become, so the first, the 100 Celsius for 1 minute, and then you have ramp 20 Celsius per minute, so it have 5 minutes there, and then you set, when it reaches 200, you set it to become constant for 2 minutes. So basically your analysis time is 8 minutes. So how does this program affect your chromatogram? So when you set 100 Celsius for 1 minute, this first compound would evaporate or would become separated instantaneously. The 200 Celsius compound will not be separated yet. Okay, once it reaches the 200 Celsius, then the 200 Celsius compound will be separated. So your chromatogram would be macam ni lah. So bila yang the first one dah elute dulu, sebab kita biarkan dia kepada 1 minit untuk 100, so dia ada masa 1 minit, and then untuk yang 200 ni jarak dia adalah 6 minit, betul? So basically yang 100 tu akan keluar dulu, and then kita ada masa lama barulah yang second keluar. So these well-resolved peaks are what that we want lah. Okay, so this is how you employ temperature programming to enhance your separation and also to get a well-resolved peaks lah. Okay, but this program also you can play around, because it is something that, okay, when it is too wide, the resolution is also not effective. That's why I say that we need to have an effective resolution or effective separation. So if it is too long, when you play around with the programming, you can minimize the time here. Kan? You can minimize the time because you can change the RAM, you can change the constant temperature, the constant time here. For example, for 100 Celsius, if you want to change to 0.5 minutes also can. For 200, you can change to 1 minute also can. So even this RAM, you can also change it to 30 Celsius per minute or 40 Celsius per minute. But you also need to figure out on what are the effective or optimum time to achieve a separation. Okay, that's how temperature programming helps you in having the good separation. Okay. All right. So this is the temperature programming profile. So as I mentioned, so you need to change. For example, you set it. Kalau based on our example here. So so the initial one, so this is going to be 100. So this is going to be 100. So you set it for 1 minute, and then you have RAM. So RAM ni kan yang kata 20 Celsius per minute tu. So this 20 Celsius per minute is going to, this is the RAM. And then when you achieve here, 200, and then you hold it for 2 minutes. So for our analysis yang our contoh tadi tu, so this is our N. But for this graph, they increase another RAM, and then they have the final RAM, final constant temperature, and then finish analysis. Okay. So these are the example of isothermal versus program temperature. So isothermal, as what we have known, isothermal straight away you think fixed, something that is fixed. Something that is fixed. Okay. Kalau temperature programming, they must have some kind of program. The what initial, what are your RAMs, and then what are the final temperature. So for isothermal, this is the example of isothermal separation of alkanes at 140 Celsius throughout. Means that they set the temperature to become 140 Celsius sepanjang analysis, which is 40 minutes. So what you would see is that the separation is well resolved for these two. C12 and C14 is well resolved, but C14 to C16 is too long. It is too long. And for C8 and C10, it is too near. So it is not an optimum. So when you apply temperature programming, okay, the temperature programming here is 50 Celsius to 230 Celsius at 4 Celsius per minute. Means that dia punya, okay, dia set at 50 Celsius and then you straight away have a ramp until 230 Celsius. Okay? So this ramp nilai dia adalah 4 Celsius per minute. So when you do this temperature programming, you would see that the analysis has become shortened. More or less, it's become like 30 minutes here. And you would see that the presence of other compounds as well, C20, C18 as well. But all of the peaks are well resolved. Nampak tak? It is well resolved. It is not too long or not too short. So that's how you use temperature programming. You can manipulate the temperature to achieve a good separation. Okay? So temperature effect on retention. So retention on retention times lah. So retention times, because on how are you going to use the optimum temperature. For example, for this, if you use 75 degrees, you would see that there is a lot of gap here. There is a lot of gap. For 110, if it is 110, the temperature is, that the chromatogram is not that good because you would see that the saturation here. But when you apply 130 Celsius, you would see that the separation is also not that good, but it is too near to each other. So sometimes we can say that this resolution is not that good. So you can use temperature programming to separate these peaks. Okay, even though it is the time taken using higher temperature is much more lower, but we would say that it is not a good separation lah. This is a good separation, tetapi it's quite long. So we also want to save time as well as save having a good separation. Maybe something in the middle. Okay. All right. So that is the column. That is the oven. And then we go straight into what is inside the oven, which is the stationary phase column and stationary phase. Column and stationary phase is the heart of the GC system where the separation occurs. It determines efficiency and selectivity. Okay, type of column. There are a lot of there are 3 types of column. First is the porous layer open tubular column, or we call it plot. We also have a wall-coated open tubular column, which is WCOT, and pad capillary column. So you can see the difference of what is plot, what is WCOT, and what is a capillary column. These columns, these benda-benda bulat ini are the stationary phase. Okay. For example, this yang benda-benda bulat-bulat ni adalah stationary phase. Ini pun all the stationary phase. Yang kalau the wall coated open tubular column, the stationary phase is embedded inside the wall. So This stationary phase lah yang akan interact with your analytes. How well your analyte interacts with the stationary phase will achieve the separation. Okay, so open tubular columns, PLOT or WCOT. Okay, PLOT or WCOT, no support material. It is used flexible fused silica, which is coated with polyimide layer. The temperature for the column, it must be lower than 350 Celsius. So means that you need to know whenever that you use PLOT or WCOT, you need to pay attention to the maximum temperature. So this maximum temperature, you need to make sure that your oven does not melebihi, exceed the maximum temperature. So the internal diameter of the WCOT or PLOT usually is 0.1 millimeter to 0.75. So the film thickness is usually 0.1 to 5 micrometer, and the column length is 5 to 50 meters. Okay, so this is important. As internal diameter and film thickness increase, the sample capacity increase, but the efficiency is decreased. Why? Okay, this is the answers that I want for next week punya class. Okay, so you need to find out why is this facts are stated here. Why would you think that as internal diameter and film thickness increase, the sample capacity will also increase, but the efficiency will decrease for PLOT and WCOT? So you need to find out why. Okay, so this is an assignment for you. Okay, all right. So let me check. Okay, packed column. It consists of three main components, which is the column tubing, the support material, and the liquid stationary phase. So the column tubing must be chemically inert, thermally stable, and must be able to coil up. Okay, usually the column tubing is copper, stainless steel, ataupun glass lah. Okay, the typical sizes is usually 1 until 3 meters long, ataupun this is the outside diameter, and then the internal diameter usually 2 to 3 millimeter of internal diameter. In the inner surface is usually silated to reduce interaction with polar analytes. Okay, this is packed column. So what are the differences between packed and open tubular columns? There are several factors that we differentiate them in terms of the efficiency, the sensitivity, on how the operation, the sample amount, and the price of buying the column. Okay, the efficiency is low to moderate, but for that is for packed column. For open tubular column is quite high. Okay, the sensitivity is quite low for packed column, but it is high for open tubular column. Operations for packed column is easy. The open tubular is not that easy. Okay, the sample amount needed for packed column is large, but for open tubular is small. Okay, the price of course is high for open tubular because you achieve all of these advantages. You would have high efficiency, high sensitivity, and just a small amount of sample used. Okay. Okay, so now we are going to look at example of using the column type and the separation. So this is WCOT, okay, wall coated open tubular. Okay, this is packed column, this is WCOT. So you can see that first of all, you need to see the retention time. Okay, the analysis time for all of the sample. For packed column, you see that the analysis time is 10 minutes. But when you are using WCOT, it is minimizes until 4 minutes. Maybe this is 5 minutes. And more separation happens. More compounds appear. Okay? All right. So, if you have any question for until now, you can just straight away WhatsApp in the group. Okay? Just ask anything that if you don't understand, so all of us can straight away give our input on it. Okay? Okay. So how column conditioning? Okay. When you have a column, any column, it doesn't matter if it is a GC column or HPLC column, you need to condition your column prior to analysis. Okay, column conditioning is something like pembersihan column lah. Okay, for example, as I mentioned before this, sometimes when a day before when your friend are using the GC, the column gets dirty with all of your friends' punya sample or analyze. So for your analysis, you need to condition it first. How is column conditioning for GC happen? So the the condition temperature, usually it is 20 degrees higher than the analysis temperature. So you just set the temperature and then you do a blank run. Okay, blank run. Blank run. Okay, what is blank run? It's just sometimes they are using just air ataupun sometimes you use a solvent to clean up your column. At least 10 to 20 Celsius less than stated maximum operational temperature of the phase. So for example, you can use this one, but also you can use this one as well. For example, the column said that the maximum temperature for the column is 250 Celsius. So when you do column conditioning, you set it at 200 Celsius, which is less than the maximum amount, less than the maximum temperature. Okay, never condition at column max temperature. These are the rules lah. Never condition at columns max temperature. In this case, never condition at 250. So you cannot do this. Okay, you cannot do 250 Celsius. You need to be use at 200 lah, which is the safest way. Okay. Program temperature to slowly reach the condition temperature, slowly rate. If you want to use temperature programming, also can, but you make sure that it is slowly rate. Means that it deny it to sikit-sikit. For example, you set it 100 to 200. So you need to make sure that your RAM here is very small as possible, 2 to 4 Celsius per minute, because we want to make sure that all of the contaminants evaporated and move out of the column. Okay, cool down slowly. These are the regulations lah. The thing that you need to follow. Purge column with carrier gas for half an hour before repeat the heating process. So the carrier gas also needs to be freely flowed before you do any analysis for about half an hour. Okay, because usually in the morning, when you want to start the analysis, you would open the gas first to make sure that the gas has been flowed through your system for about half an hour. Okay. Use a very high carrier gas flows for conditioning. So these are the things that you need to know, but usually we have the column conditioning procedure in the lab lah. So you need to follow the SOPs. Okay. Condition time depends on analysis. So if your previous analysis will require half an hour of analysis, maybe you need some more time for conditioning lah. Okay. All right. So the GC columns and stationary phase, I think that this has been in your been taught in your instrumental analysis class, but I'm not sure whether I should cover it or not. Okay, let me just go through lah. Okay, so factors in selecting your stationary phase. So you need stationary phase means that your column lah. Okay, so you need to know the nature of your analytes. You need to know the stationary phase type. You need to know your column internal diameter, the film thickness, and column length, because all of this will affect your analysis. Okay, so as an example, column length. Kalau you buat separation pada column yang panjangnya 30 meter and 60 meter, apakah perbezaannya? You would see that the 30 meters punya column length, its retention time will be much more low, which will be much more shorter than the 60 meters, because it takes more time for the analyte to go through 60 meters length as compared to 30 meters length. So sometimes this column length is also important for you to save time, but also you need to know that sometimes for 30 meter, it is not enough for the separation to happen. Sometimes that's why we opt for 60 meters. So all of this, apa tu orang kata, all of this temperature is, temperature pula, all of these parameters are important. Okay. Okay. Type of stationary phase in open tubular columns, whether it is a WCOT or PCOT. Non-polar columns, polar columns, you need to know, depends on your analytes. The separation according to the analyte volatility, you need to know the retention times increases with boiling point and retention time increases with chain length. Okay, so the length of the column also plays a role. Polar columns, separation according to volatility as non-polar and according to the polarity for polar analytes. Polar analytes more highly retained compared to non-polar of the same volatility because you are using polar column. So this is like, dissolve like principle. Okay? Interaction by hydrogen bondings or dipoles. Order of addition can change between types if analytes in the mixture have different functional groups. So all of these, parameter you need to know to ensure that your separation would be efficient and effective. Okay. All right. So non-polar stationary phase. Okay, we are going to look at non-polar stationary phase. Non-polar stationary phase usually hydrocarbons packed in column only. So for example, apizin L, which consists of just CH2 and it is a polymer. Squalene, apoline. So basically all of these are hydrocarbons. So you know that hydrocarbons are non-polar. Okay, we also have Agilin SE, which is 100% dimethyl polysiloxane. Agilin HP1 also is 100% dimethyl polysiloxane. Okay, so we also have a 5% phenyl for methyl polysiloxane. So all of these are example of a non-polar stationary phase. Okay. For polar stationary phase, usually it is Agilin DB23, Agilin HP88. So usually the stationary phase is made up from cyanopropyl or cyanoethyl. Okay. ideally suited for fatty acid metal esters. So that's why I said initially, when you have a sample, you need to know that what is the right column for you to use. You already know the theory of it. Okay, I have a non-polar analyte, so I need to use a non-polar column, but which column is the best for me? So sometimes these companies have created a column which is suitable for some analytes. For example, if you want to analyze fatty acid metal ester, you will need to use either these two, which is a polar stationary phase. Okay? Right. These are other examples of polar column. Okay. Let's look at the chromatogram. GC on non-polar liquids. So gas chromatography using non-polar liquid phases, which is, for example, is ultra 1, 100% dimetal polysiloxane. These are the dimensions: 25 meter long, 0.2 millimeter internal diameter, and 0.33 millimeter film thickness. So these are the analysis of hydrocarbons. Hydrocarbons non-polar. So you will see that it employs temperature programming here. Okay, so 50 Celsius, and then you increase up to 230 Celsius for 2 minutes, 2 Celsius per minute. So you would see that the separation happens according to number of carbons, isn't it? So C8, we would definitely think that C8 would elute first because it has the less number of carbon, means that it has the lesser boiling point, the lower boiling point. Okay. GC on relatively polar liquid phase. Now you are going to separate hydrocarbons by using a polar column, which is in this case column carbowax 20M, which is a polyethylene glycol stationary phase. It employs the same temperature programming. Okay, it employs the same temperature programming, and the film thickness is this. I mean, the dimension of the column. So you would see that sometimes using another type of column would decrease your analysis time. For example, when you use a non-polar column, the analysis for achieving C22 is about 70 minutes. But if you are using a polar liquid phase or polar column, the analysis time is about 40 minutes, which reduces 30 minutes of your analysis time, which in this case would save your gas. But you need to know that the separation happens is, for example, this C8 is too close to your solvent punya peaks. Okay, and the concentration or the peak height of all of the compounds is quite the same as compared to here. Okay, for example, you can see that a very big distinction of C22 is quite high. Means that you were able to separate more here. You were able to get more more concentration here as compared to just using a polar liquid. So in this case, I would say that you need to find out what is the best column for your analysis, for your analytes. Sometimes using polar column would have an advantage, but if the advantage mengurangkan you punya concentration yang sepatutnya, so it is not good. Even though you can save time, but it is not good. So you need to find some, apa orang kata tu, something in the middle of having a good separation, having a good concentration of your analytes, and also save time. Okay, you need to find something in the middle in this case, because this is 100% non-polar, this is 100% polar, so you need to find something in the middle. Okay. So these are the example of other examples of essential oils for other compounds as well. So this is the essential oil for using on polar liquid. So there are also columns specified for acids and specified for bases. So there's also a chiral column. These are the specialized column lah. So if your analytes are all of these compounds, you might need to think about using this column lah. Using this column. Okay. All right. So this is also an example of a separation of free fatty acid by using BP21 column. Okay. All right. This is also example. This is also example. Okay. So effect of column length. This is effect of the column length. As I said, can greater length gives resolution. Greater length give resolution, but retention times are longer and prone to peak broadening. So 15 meters, you would see this kind of, for example, 15 meters, you would see this kind of chromatogram. 30 meters, you would have this kind of chromatogram, and 60 meters, you would have this kind of chromatogram. So which one is better? In my opinion, the 30 meters is much more better because you achieve a good resolution but also didn't suffer a very long retention time. Okay, so you need to find something in the middle lah, in terms of choosing the right column. Okay, the right column with the right length with the right polarity. Effect of column ID also, column internal diameter also would affect your separation. So this resolution is too big. This resolution is just nice. Okay. Usually we will achieve we want R equivalent to 2 lah. Okay. So this internal diameter is much more better. Okay. Effect of coating thickness pun, the coating thickness also would achieve, for example, for this one, in my opinion, this one is much more better. The 0.5, this is too wide. It depends on you. It depends on what you would think is the best. Because for some people, they can accept this, but for some people they choose this one, and some people they want a very broad because maybe they have a luxury of time. It depends on you. It depends on you, but make sure that your separation is effective and efficient. As it says here, greater film thickness gives increased resolution and increased loadability, but reduce efficiency and prolong retention times. Okay. Okay, detector. This is the last part, I think, for the detector. Okay. So detector, different detectors will give different types of selectivity. Okay, a non-selective detector responds to all compounds except the carrier gas. Okay, a non-selective detector. A selective detector pula responds to a range of compounds with common physical or chemical property, while a specific detector responds to a single chemical compound. Okay, let's see. Flame, okay, these are the examples of detector. The one that is the most used is flame ionization detector, where it detects organic compounds. But if you want to have a universal detector, usually we use thermal conductivity detector. So this thermal conductivity detector, we can say that it's a non-selective detector. Okay. But for example, electron capture detector would only detect halides, nitrates, peroxide, and hydrides organometallics. So if your samples contain all of this, if your analyte is halides, organometallics, you would need to use ECD. We also have other uh, types of detector as well, which only detects certain things only. Okay. All right. So troubleshooting in GC, these are the problems that you would face in the GC. I would suggest that you would look through all of this YouTube link, because you would see that, for example, this is a normal peaks, but this is a problem peaks because it was supposed to be this sharp, but this peak have a peak broadening. Okay, the peak broadening problem. So it is not, for example, for this one, it is not well resolved. So how are we going to resolve this? And then, for example, when you see this kind of peaks, kan dia naik and then dia turun, tapi ada macam bump dekat sini. Ni pun ada bump, ni pun ada bump. Usually there is another peak here. So all of these issues you can find out in the YouTube video. Okay, how to solve fronting issues. So this is normal symmetrical peak, as I mentioned before, kan? So this is tailing, where it was supposed to be to instantaneously increase, and then it was supposed to become down like this. Tetapi we have a tailing effect here, and we also have fronting effect here. So how are we going to resolve this? All right. So this also might be, I would say that, okay, this also might be an assignment for you to, we can discuss it during next week class. So this is an assignment for you also to look at the videos and then come up with a table on how to solve all of these issues. Okay. Okay. So for example, some of the issues related to these problems, maybe you are using the wrong mobile phase. If it is too strong, sorry. The flow rate is too fast. Okay, the flow rate of the mobile phase is too fast. You are using the wrong pH. You are using the wrong column, or the column temperature is too high. Okay, for example, if you see that your baseline, when you do conditioning, when you see your baseline, it was supposed to be like this. Okay, when you see a baseline, oh my god, it was supposed to be straight. Okay, when you see your baseline straight, and then towards the end, dia naik macam ni. So this we call column bleeding. Column bleeding, column berdarah. Okay. What does it mean by column bleeding is that towards the end of your analysis, towards the end of your column conditioning, your stationary phase is already started to elute itself from the column. So it means that the temperature is too high. So it's too high, makes your column or makes your stationary phase come out of your column. Okay, so so you need to evaluate lah all of this to make sure that the problems have been rectified. Okay. All right. So maybe I think that in terms of for this slide, I can stop here. So maybe I stop share first, and then all right. Thank you guys. I will continue with the next slide.